This is a demonstration of using CodeBench Virtual Edition, an extension to the Mentor embedded Sourcery CodeBench integrated development environment, to debug embedded software at 3 different stages of a project. First, we'll show how a Vista Virtual Prototype can be used to begin debugging software before the hardware is designed, and for testing architectural assumptions and decisions. Then we'll show how hardware-software co-debug on a Veloce hardware emulator can reveal hardware defects arising from complex hardware-software interactions before the hardware is taped out, and while there's still time to fix the hardware. Lastly, we'll show the same debug environment running on a prototype board using a JTAG probe. This is the Sourcery CodeBench IDE, where embedded software developer would edit his source code and compile it into the final executable program. On the right side, we can see everything defined in this module. By double-clicking on main, I can move the viewpoint to main. Now I'll finish writing my code, save this file, and build my application. Once the program is built, I can debug it with a number of different execution vehicles, including Vista Virtual Prototype, the QEMU target, Veloce RTL emulation using CodeLink, Veloce RTL emulation using a virtual JTAG probe, FPGA prototype using a JTAG probe, or the final board using a JTAG probe. In this case, since I haven't got any hardware, I'll choose to debug on the Vista Virtual Prototype. Now CodeBench starts the virtual prototype simulation and the debugger and moves into the debug perspective. As I step through the code, changes to variables are highlighted in the variables view. Now I'll step over the initialization code up to the basic packet test. Now I'll step over the basic write function. 10 bytes were sent. And I'll step over the read function. 10 bytes were received. The status OK indicates that they were correctly received, so the basic packet test worked fine. So now I'll step a little bit further, clear my counters, and start a long packet test. In this case, I sent 65 bytes, but it reports 66 bytes because the write function appends a null terminator to the packet. Now I'll step over the read function to read the bytes, and something went wrong. I got a status bad and 0 received bytes, so something went wrong with my test. A casual inspection of the code reveals the source of the problem as a cut and paste error. I already finished the basic packet test and I'm trying to do the long packet test, and I called the long write function but the basic read function. So now I'll quit the debugger and fix my code bug, save the file, and rebuild it. By clicking on the debug button, CodeBench will rebuild the application first, then relaunch the virtual prototype simulation, relaunch the debugger, and take us to the beginning of main just like before. Now I can step over the initialization code and step over the basic packet test. 10 bytes sent, 10 bytes received. Clear my counters. Step over the long packet test. 66 bytes were sent. 66 bytes were received. The status is OK. So the long packet test works too now. So we'll move on. The next thing is we go into a loop sending a lot of random sized packets with random data. So I'll set a breakpoint at the end of the loop and I'll run through the whole packet test loop. Now I've hit the breakpoint, and by checking the status is still OK, I know that my random packet test passed. So now I can carry on with debugging the rest of the functionality in my system. Advancing the software development schedule using simulation platforms such as QEMU or Vista provides obvious benefits to the overall project schedule. Using Vista Virtual Prototype also enables system analysis capabilities to ensure the design will meet performance and power budget requirements. As the software runs on the virtual prototype, execution is logged alongside estimated power consumption to show power usage over the run correlated to where the code was executing at any given moment. The Sourcery Analyzer perspective allows me to look at a number of performance metrics by picking from the Sourcery Analyzer agents list on the right-hand side. Here I'm looking at the function call graph, which shows me where my code is executing, and I'm looking at the VP power analysis graph, which shows me how much power is being consumed. One thing I notice in the power analysis graph is a repeating pattern of higher and lower power readings, and it seems roughly correlated to the function call activity shown below. So let me zoom in, and yeah, there seems to still be a pattern. Let's just look at 4 periods. And we can definitely see a correlation between function call activity in the bottom graph with periods of higher or lower power consumption in the upper graph. By adding function call traces below the power analysis graph, I can see what functions are active during the periods of high power usage. Here we see that when we're frequently calling the rand function, the power is higher than at other times. Since frequent calls to the random function seems to be responsible for the high power consumption, I'll rewrite my application to reuse a pre-computed buffer of random data instead of regenerating the random data on every loop iteration. After optimizing the software and rerunning the performance analysis, the power graph looks much less variable than it had in the first run. Zooming in, I do still see some power spikes associated with calls to the random function, but the power spikes are much narrower now because we call the random function much less frequently. The power analysis results from the optimized code certainly look a lot better, and by using the measurement tool, we can quantify just how much better. In session 1, the measurement tool shows an average power consumption across the run of about 117.5 milliwatts. By comparison, in session 2, the average power consumption over the run was 101.5 milliwatts. That equates to about a 5.6% improvement in power consumption.
When we run this time, we will be running on an RTL representation of the design in the Veloce emulator. When we execute this launch configuration, it will initiate an emulation session on Veloce and connect CodeBench Virtual Edition to it. We can immediately begin debugging our software. We can see the source code, registers in the processor and in the RTL, the contents of memory, and variables. We can also set breakpoints. Here I'll set a breakpoint on the function main and run out to the start of the application. We will run through the same tests we ran against the virtual prototype. As you can see, the short FIFO test completes successfully. Next, we move on to the multi-packet test. Here we see it succeeds as well. Next, we will test the FIFO with a series of random-sized data packets, but the 594th random test does not complete as we expect it to. Stepping through the inner loop of the test, we see that the outgoing data is reported as sent correctly, but when we try to read the FIFO, it is empty. If we look at the status register in the FIFO, we can see that the empty flag is not cleared, even though we are clearly writing data to the FIFO. Even if we repeatedly write to the FIFO, this status bit never updates. Although we were able to successfully process over 500 random data packets, something went wrong with this one. It appears that the hardware is locked up for some reason. Now we need to look at what's going on in the hardware. Veloce gives us that visibility. This is the waveform view from the emulation. The cursor, the vertical line in the center of the window, allows us to correlate the state of the software with a point in time in the hardware. Moving down to the signals on the FIFO, we see that there is no activity after the failing test. Looking earlier in the emulation, we can observe the data from the short test and the multi-packet test flow through the peripheral. We can also see the FIFO seem to lock up. Interestingly, there is an interrupt to the processor which occurs at about the same time that the FIFO stops working. Back in CodeBench, we can see that there is an interrupt service routine in the application. When it is triggered, it does make an access to the FIFO's control registers. This might be contributing to the cause of our problem. Further investigation will require looking at the HDL of the FIFO itself. The hardware team examined the HDL and found that there was a register which was sized too small. It was overflowing and locking up the FIFO in the unusual circumstance that the interrupt occurred exactly when the FIFO was full. Increasing the size of this register should fix the problem. With the HDL for the FIFO fixed, we can rerun the tests and see if everything is now working correctly. We will once again choose the launch configuration, which will initiate an emulation session and run the software on the HDL representation of the design in Veloce. CodeBench Virtual Edition connects to the emulator and allows us to begin debugging, as before. This time we will place a breakpoint at the end of the tests and see if we successfully run everything. Even though we ran all these tests with the virtual prototype earlier, we did not see this problem, as it was an RTL coding error. It is important to be able to run the same software against different levels of abstraction of the hardware as the design progresses. Here we see that we are able to completely run all of the tests successfully.
By this point in the project, we've completed our architectural analysis and functional verification on virtual prototypes, and we've debugged the actual hardware implementation on a Veloce emulator box. So now we get our real board back, and we connect the JTAG probe, and we're ready to start debugging again. This time we'll pick the final board using a JTAG probe. We're in the debug perspective again, and as we step along, the variables are changing. We complete our basic test successfully, so we step on to complete our long packet test. That completes successfully as well, so now we'll run the random packet test all the way up to the breakpoint we had set before. So the random packet test completes successfully, and everything looks good. We've been able to cut our development schedule substantially by doing a lot of our debugging up front. And at this point, we just need to retest the results on the final board in a real-world scenario.